So in the last lesson, we talked about the advantage of creating a power series function. The first advantage is it allows you to graph it. If you need to, take a look at it on your graphing calculator. You can't graph the sigma, but you could graph the power series, and they would be virtually identical. You would not notice any difference between them. The other advantage, being able to create a power series function, is that it's a lot easier to find the derivative and antiderivative of, which is going to have advantages for us too. So that's what we're going to talk about this time, as to how to do a derivative and an antiderivative, because you can't do it to a sigma, but you can do it to the other one. Okay? All right. So here we go. Okay, so suppose you are able to find the power series for the f of x, and you define it as a sub 1 over 1 minus r of x. So you're able to find that. From there, you can do various antiderivatives. So suppose you wanted to do the integral of that. Well, then that's going to get you capital f of x plus c. And you're going to find that by doing the integral of the format of the power series sum. So you'll do of a1 over 1 minus r of x dx. And depending on what that's going to be, it's probably going to be a natural log. So it'll be a1 times the ln of 1 minus whatever r of x is, divided by -1 for your chain rule, and then plus c. So you're allowed legally to do that. You also can take your power series and find a derivative. So you can just imagine we're going to do position, velocity, like we're going to do all the things, only we're going to do it with, we're going to do area, we're going to do all the stuff. All right, so we're going to take a derivative. If you take a derivative of this, you'll find f prime. And so that would be finding the dx of a sub 1 over 1 minus r of x. And since a sub 1 is a constant, it's going to be a sub 1 times 1 minus r of x to the negative a sub 1. That's the derivative. Pull the power down to the front, decrease the power, and then remember the chain rule, which is going to tack a -1 on the end. Okay, so this is what you're allowed to do to series. Okay, so we're just going to take our first stab at it. So first, let's find the function represented by this series. So our function would be, we'll just generate the terms. If we plug in 0, what's the first term? 1. Second term will be x, then x squared, then x cubed, then ... And this can be summarized as the following power series function. So what would the numerator be? 1, and the denominator would be 1 minus x. So that's the lessons leading up to this. Now in the next slide, switch over, we're going to take that. Since we know that, now we can do the derivative on both sides. So we can say, okay, I'm going to do a dx and take the derivative of all of this. So we can start with all the derivative pieces. What's the derivative of 1? 0. What's the derivative of x? 1. And then what would be the next one? 2x. And then 3x squared, and then ... And that should be, it is, equal to the derivative of, so we're doing the derivative of what do I want to do here? dx of the middle. And we're going to do the derivative of the last part. So to do the derivative of the last part, you want to think of that as 1 minus x to the -1, and you want to take the derivative. So that would be pull the -1 to the front. 1 minus x goes to the -2. The chain rule adds on a -1 to it. So overall, we are left with 1 over 1 minus x squared. And those two things will be equal as well. So just as in the original polynomial that was infinite, 1 plus x squared, just as that was equal, what did I do?
-1 over 1 minus x squared, or no?
We multiplied by the chain rule also.
Oh, okay, got it.
And so that should get us a positive. I think we had a double negative to get us a positive. Okay? Okay? So the long polynomial starts out as equal to 1 over 1 minus x. Its long polynomial derivative starts out as 1 over, or ends up to be 1 over 1 minus x squared. So legally allowed to do that. You can also do the antiderivative on all the pieces. So you do the antiderivative of the left part, the middle part, and the end part, and those should be equal too. So if they start out equal, then the derivatives have to be equal, and the antiderivatives have to be equal. Derivative would be -1 times 1 minus x to the -2 times the chain rule of -1.
Oh, yeah.
Yeah? All right, great. Okay. This is just the formal way of writing, like, notice here, this is, oh, move the power down to the front and decrease the power by 1. I mean, it's all the same thing. But the conclusion is, a series will converge if it has a derivative that converges. A series, whoops, that doesn't make grammatical sense. A series that converges, that's better, has a derivative that converges. That makes more grammatical sense. This is not true for divergency. I cannot say the same thing for divergency. Only convergency. If the series converge, the original series converges within the interval from -1 to 1, then its derivative will converge from -1 on that same interval of convergence. But you cannot say it about divergency. There's no guarantee. This is a guarantee, but divergency is not. Okay, so we can also do the antiderivative. So since we know that this expression is defined as a power series, we can integrate both sides. So we can throw an integral here, and we can throw an integral over each piece, and we can throw an integral on that side. So to integrate all of the pieces, the integral is going to get us to, the integral of 1 is x. The integral of x is half x squared, 1/3 x cubed, 1/4 x to the 4th, ... All of that would be the antiderivative of 1 over 1 minus x, which is the negative ln of the absolute value of 1 minus x plus some constant c. It's negative, again, because of the chain rule. So let me get back to the advantage. It is not possible for you to graph x plus half x squared plus 1/3 x cubed plus 1/4 x. Why is it not possible for you to graph that? There's no end to it. It just keeps going and going and going and going. But you can graph the negative natural log of 1 minus x. And they are essentially equal in every single way. Now, how would you solve for your plus c? What would you need to know? Yeah, some kind of initial condition or something you'd have to know to find your plus c. Okay, but you are allowed to integrate everything and still have equality, yeah.
Where would we find that initial condition? Would it be given?
Mm-hmm. Mm-hmm. All right, so the same thing is applying here. A series that converges has an integral that converges. So that is also true. But again, once again, divergency is not a property. Just because the series diverges doesn't mean diddly squat about what the integral may or may not do. Okay, here we go. If you are given an original power series, and you're given both its sum expression and its expanded expression, so you have both sides of it, and you're told this, which the implication of that is convergency. This is the interval of convergence. So if you're given an interval of convergence, we know that convergence applies not only to the original one, but it's going to apply to any derivatives or antiderivatives we do as well. And you're asked to find a power series that would represent ln 1 plus x. You just need to recognize the relationship between this expression and that expression. So what direction are we going to go from what we're given to what we're trying to find? How are 1 over x plus 1 and the ln of 1 plus x related to each other? Yeah, they are related. One is the antiderivative of the other. So if those two are related as an antiderivative, then we should be able to find the antiderivative of all the pieces as well. All right, so here we go. ln of 1 plus x, we know to be the antiderivative of 1 over x plus 1 dx. So it must also be the antiderivative of all of these pieces. Okay, so it must be, what's the antiderivative of 1? X minus the antiderivative of x is half x squared plus the antiderivative of x squared minus the antiderivative of x cubed plus dot, dot, dot. And now, what is the antiderivative of negative x to the n? So let's follow our rules. How do we find the antiderivative of that? Well, what do we do to the power? We have to add 1. What do we do with that value? Divide it. And what do we do with the chain rule? Okay. We also have to divide, because we're doing antiderivative, by the chain rule of negative 1. In other words, the sum of negative x to the n plus 1 divided by n plus 1 and negative 1 as n starts out from 0 to infinity. And what can you claim about the convergency property of what you just found? It will converge. Okay, because the original power series we worked with converged, this one will converge as well, because it comes from a converging series. If it's coming from a converging series, it will also converge. If it comes from a divergent series, it may or may not. We don't know. One other thing I want you to, yeah?
How did you find out that n equals 0?
I just,
What equation did you plug in?
well, I plugged it into this, and I just asked myself, what would I plug in to make sure that my first term starts out as x? Okay? And so if I plug in 0, if I plug in 0 here, and I plug in 0 here, I'm guaranteed that the first term is going to be, well, the numerator would be negative x, and the denominator would be negative 1. So I'd get x as my starting value. Just one thing to point out, the original series is geometric as well, because it has the constant multiplier of negative x to the n. But that doesn't mean that the antiderivative is going to be geometric. Our antiderivative is not geometric. So just because you start with a geometric series doesn't mean that your antiderivative will be geometric. The only property that is preserved is if you start with a converging series, then the antiderivative will be converging as well, but not the property of being geometric. Okay, let's try another one here. Find both. Find both, yeah.
Will it tell us that it converges, or?
It's implied that it converges by the fact that we got an interval of convergence.
Okay.
All right, find a power series for both f prime and the antiderivative of f of t if we're given this power series here. So before we can find f prime, the derivative, or the antiderivative, we need to have a function to do the antiderivative of. So we're going to start with looking at what this expands to first. So if I start with 0, I get negative 1 to the 0 times x plus 2 to the 0, and then negative 1 to the first times x plus 2 to the first, and then negative 1 to the second times x plus 2 to the second, etc., 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 which will leave me with approximately what overall expression? Okay, Alex, you want to try it? What overall power function, whatever function would this be approximated by? 1 over 1 minus, how about the negative 1? Okay, so 1 minus negative 1 and x plus 2. That's our r this time. All right, our r of x is both the negative 1 and the x plus 2, both of them. Okay, so how would you simplify that, Alex? 1 over, good job, x plus 3. All right, so that is the original power series. Now I should be able, so this is what we're calling our f of x. So from that, we should be able to find both an f prime and we should be able to find an antiderivative. So let's just find our f prime first. So our f prime is going to be all the derivatives here. So let's start with, what's the derivative of the first piece? 0. What's the derivative of the second piece? Negative 1. Okay, very good. Not positive 1, but negative 1. Okay, the derivative of the second piece, is it going to be positive or negative? Should be positive. And what is it? 2 times the quantity x plus 2. And if we had another one, it would be negative again. It would be 3 times the quantity x plus 2 squared. Now we could take that on and on and on forever, plus dot, dot, dot. But I'd rather find the derivative of 1 over x plus 3 instead. So the derivative of 1 over x plus 3 is going to be negative 1 over x plus 3 squared. So there's where we've got a huge advantage in that we just, instead of having this infinitely long polynomial, we just have a single term we can find its derivative of. Okay, and then what would capital F of x be in terms of the antiderivative from a to x of the original function. So then again, we're looking back to the original expansion and we're finding the antiderivative of that. All right, so what is the first term if I'm finding the antiderivative there? Careful, look at the original term. Okay. So we've got, this is gone, right? So that's just 1. But what's the antiderivative of that quantity? X plus 2 to the 0. What's the antiderivative? X plus 2 to the first. Yeah, did you say that?
No, I said x.
Yeah, it's not just x. It's x plus 2 to the first. And the next one, what?
Why isn't it x? Because isn't it x plus 2 to the 0, 1? So then wouldn't the antiderivative of 1 just be 1?
If you simplify it, that's why you need to leave it in its expanded form.
Oh.
So that's why I, when I'm taking the antiderivative, it's what it originally was. It's not what it simplifies to. It's what it originally was. Okay. All right. Okay, so then the next part, what it originally was. I'm taking the antiderivative. So we don't do anything with the constant. The constant's still a minus, and then it's going to be x plus 2 to the what? Squared, and then divided by 2. And then the next one, x plus 2 cubed divided by 3. And then dot, dot, dot. And then we would have, okay, could that be expressed as? And that's going to be expressed as the natural log of the absolute value of x plus 3 plus some constant c, which I could find if I had my initial condition. So again, the advantage here is that while you cannot graph or make a table for the parts of it that are infinite, you can make a graph or a table for the parts of it that are expressed either as a fraction or a natural log. So we have something that is infinite being able to be approximated by something that is finite. It's terminal, it ends. And all of them converge as long as, and so this is what Edson was asking about, these will all converge if what is true from the very, very beginning?
R of x is between.
Yeah. So the only way that so don't just say, yes, they'll all converge. They will all converge if. And so the R of x has to be between 1 and negative 1. Our R of x is negative 1 x plus 2. Divide everything by negative 1 and change all the signs. And subtract 2. So our x has to be between, centered at negative 2, radius of negative 1, or 1, radius of 1, and then bounded between negative 3 and negative 1. So yes, all three of these will converge as long as x stays within what it's supposed to stay as.